Hello students, and welcome to another video. I'm your teacher, Mr. Flynn, and today we're going to be in Chapter 4, Section 5, and we're going to be focusing on the properties of water. So for all of the sections on here, let me get my pen going here. All right, we're going to be focusing on all the ones that say 4.5, okay? All right, so let's get into this, and let's just have a conversation about it. In this first example, we have liquid versus frozen water. And what we can see here is when we have the liquid water, the atoms, the molecules of water are freely moving around each other, and they're much closer together than they would be in a frozen state, because when they're frozen and they're just vibrating in place, they actually lock into these lattices. And because they make these lattice shapes, it actually pushes the atoms away from each other, making them less dense because there's less atoms per unit area. Like, for example, if these circles are the same size area, we have 1, 2, 3, 4, 5, 6 atoms here. And then on this side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12. I don't think it's necessarily this drastic, but the illustration is to prove the point that we're fitting more water molecules in a given area when they're in a liquid state than when they are in a solid state. Now, this is unique to water. Most states of matter, when you go from a gas to a liquid to a solid, they become more dense. Water, on the other hand, goes from a gas very not dense, okay, to more dense, and then it goes back to being less dense as a solid. So when we're looking at why ice floats, this is the reason, is when those water molecules form these hydrogen bonds, this bond that exists between these two water molecules. All right, we talked about this previously in the video before, and that's the driving force of why water is less dense when it's frozen. And these hydrogen bonds are caused because water molecules, like the one right here, okay, has a positive and negative end. It acts like a small magnet. And when these small magnet-like molecules get near each other, they form a bond, and this bond is called a hydrogen bond, okay? Now, I like to differentiate between bonding and forces. This is more of, like, in my mind, a force. It's between two molecules. Bonding is happening like inside of the atom itself, but the inside the molecule between the atoms. And then between these molecules, we have these forces that exist, and this was just called a hydrogen bond because there's hydrogens with our water molecule, okay? And that's what's driving this states of matter down below that we're observing, okay? Now, when we go to the top here, these hydrogen bonds exist, and they're bonding here, and I've just drawn this illustration to kind of show that it's making like a bridge, all right? And these little bonds here are sticking together, and we call this surface tension, when like a skeeter bug can sit on the surface of water without breaking it. If you were to step out onto water, you would break the hydrogen bonds because they're relatively weak compared to you putting your weight on the top. But these skeeter bugs spread out over the surface, and they're actually supported, and they can walk on top of the water, and that's because of the hydrogen bonds. And we just call this surface tension. And once we break surface tension, the skeeter bug will fall through, okay? And there's ways that we can break surface tension, and that's with like surfactants, which we'll talk about below. Okay, now you got to recognize the hydrogen bond is what's driving all of this. It's because there's a positive and a negative end to our water molecule because of the distribution of how electrons are shared and how oxygen is hogging those electrons, and it creates that dynamic of positive and negative. And that's what's driving all of these characteristics. And so here's another characteristic, and we have something called substrates. So substrates are when water interacts with a surface. So for example, if we have a wax surface or a leaf, right? Leaves kind of have waxy surfaces to them, all right? The water molecules don't interact with the surface because water likes to interact with things that act like water. So if we have like a magnet, it's not going to stick to a marker, like a plastic marker, because markers don't have positive and negative ends like a magnet does. So they don't interact with each other. And it's like the water molecule doesn't want to interact with the surface. It'd rather stick to itself and do something called cohesion, where water sticks to itself. Now, when we go to the spectrum here, we go to the far side, to this right side, we have glass and metal. They are very polar, meaning they have surfaces that have positive and negative ends, and water as a magnet wants to stick to those surfaces, and so it spreads out and it becomes flattened. So if you've ever seen a water droplet on a piece of wax paper or a leaf, it's all balled up and it's tightly held together. And when it's on metal or glass, it's all spread out and flattened. If you've ever driven down the road in your car and it's raining, you'll see a little rain droplet sticking to the glass, and it's just holding on. It just won't let go, and it's just streaking across the window as it goes by because water's attracted to the surface of the glass. If it wasn't attracted, it would just roll right off the glass, but instead it's attracted to it because glass is very polar, meaning it has a positive and negative end. Plastic is somewhere in between that, so it doesn't deform as much, but it still deforms. So there's kind of a spectrum here between nonpolar and polar surfaces. So if the surface has got a charge to it, like a polar and nonpolar type atoms are there, you're going to expect water to interact with its surface and to kind of deform and flatten out. Now, the other way of looking at this is called surfactants. So let's just assume that each of these surfaces here is like wax paper or a leaf. Okay, so if there's no surfactants, okay, a surfactant is something that has a polar and a nonpolar end. So it's usually a large molecule. Typically, we associate surfactants with soap. Like, this is how soap works. All right, so how soap works is what it can do is it causes things to become wet. And how it does this is the polar end interacts with the water, and then we have these tails that are sticking out, and what it's doing is it's breaking up those hydrogen bonds. When you break the hydrogen bonds, well, now the water molecules can't stick together as well, and they start to deform, and then they kind of spread out and disperse themselves. And what soap does is it sticks to dirt and other things, and it can pull it away from the surface, right? I have a video on this that you can watch, or you should have watched at the beginning with the spark, the video that was available at the beginning of this unit to kind of see how soap works. And a soap is a surfactant, right? And so what's happening is that surfactant is causing the hydrogen bonds to break, and it's breaking up that surface, and it's causing the water to kind of distribute over the surface. Okay, so one way of looking at it is a substrate, which is the surface, and then for surfactants are what causes water to break its hydrogen bonds. So we're just looking at how hydrogen bonds interact with surfaces and how when we put certain substances in, they interact with it, causing it to spread out. Okay, all right, so just think of it as soap is breaking hydrogen bonds versus substrates, the surface is breaking the hydrogen bonds and pulling them apart. Okay, now the last part, there's two more parts to this, but the main piece that you need to understand, it's one of the key things you need to know, is what is a solution. So a solution is made up of two parts. We have a solvent and a solute. So a solution has a medium which dissolves particles, which in our class it's mostly going to be water. That's why we call it an aqueous solution, meaning it's a water-based solution, and it can dissolve things. Like, for example, if I had table salt and I put it in water, the salt crystals will disappear, and the reason they disappear is because the solvent, water, is breaking them apart, and it evenly distributes them in a solution. Okay, so if we didn't have solutes and it was just pure water, just a pure solvent, it would not be a solution. It needs to have two parts. It needs to have a solute, the thing being dissolved, and the solvent, the thing doing the dissolving. Okay, and in our class, most solvents are going to be water-based, or it's going to be a water-based solvent. Okay, you may have heard of things like nail polish remover. If you're like trying to remove your nails that you've done, or those coatings that you put on your fingers with the different colors. Sometimes you have to use something called acetone, which is a strong solvent, and it will dissolve that coating on your nails. You shouldn't be getting the acetone on your hands. It will dry them out and cause them to crack. It's not good for you. But when you put it on your nails, it helps in the keratin in your nails is strong enough to kind of withstand the harsh acetone, that heavy solvent, but that acetone is dissolving that nail polish on your fingers. So there's another way of looking at it, but in our class, we're going to do a lot of dissolving with water, and the reason water works is because water acts like a magnet, and it sticks to things, and it will pull things apart, and we'll talk more about it as the year goes on. Okay, the last thing is electrolytes. Now, you've probably heard of electrolytes if you're playing sports or if you've done events where you're like, I need to have more electrolytes. I need drink. I need my Gatorade. I need my Powerade. And Powerade is a fancy drink that has sugar and salt, and that's really all it is. And they put enough sugar in there to kind of cover up the salty taste. And when you put, for example, NaCl, a solution, okay, in a beaker of water, electricity can then be conducted across the current. So how a battery is sending electricity around to this wire, and there's a gap here. You see how there's, oh, I messed up on my drawing there. Oop, come back to me. All right, so right here, there's a gap that's existing. Let me use a different color. Maybe we'll stick to red. There's a gap here that's formed between this metal wire and this metal wire across. And NaCl can actually bridge the gap because the Na can be attracted to the one side and chlorine can be attracted to the other, and it can conduct a current. So that's why we say ionic bonds, typically metals and nonmetals, when they're dissolved salts in water, they can conduct a current. And your body utilizes this to send nerve signals throughout your body and in your muscle cells. And when you sweat, you lose electrolytes, so you need to replenish them. And the idea is Na and Cl can continue to conduct the current across the gap. Other solutions like sugar, okay, they don't form electrolytes. They're large compounds. They are polar, but because they don't dissociate into little ions like Na and Cl, they will not conduct a current. So light can be conducted through that current, okay? All right, so as we're looking at these examples, okay, we're looking at the properties of water, okay? Water can't conduct electricity, but it can cause salts to be dissolved, which then can conduct electricity. All right, so we're just looking at that property. We're just saying, oh, water can allow electrolytes to conduct a current, okay? And just be aware that not everything that dissolves will conduct a current, okay? Because we have to be able to have those electrons flow through the wire to power our light, okay? Now, if we can't have them conduct, we're not going to power our light, okay? So these are the big concepts about water that I want you to kind of build an understanding of. And as you practice and work through some of the problems, you're going to get a better feeling for these kind of phenomena, okay? So just as review, water is less dense in a frozen solid form than it is liquid, and that's what causes it to flow. When water and hydrogen bonds stick together, we can create something called surface tension, where water holds together and makes little bridges that allows bugs and other things to sit on, okay? We can break hydrogen bonds with the surface called a substrate, and we can also break hydrogen bonds with surfactants like soap, which causes the hydrogen bonds to break, all right, and it causes wetting. We can create solutions with water, okay? We can put stuff in solution, and it can become a solute inside of a solvent, and together they form a solution, all right? And sometimes these solutions can conduct electricity, and we call those electrolytes. And so these are all these kind of big ideas that I want you to kind of grab when we think about and talk about water. Water is essential to life, and it's essential to a lot of the functions that a lot of the phenomenon that we see in today's world, okay? All right, thanks again for watching. Till next time.